Welcome to the Gatan EELS and EFTEM Training School. This is lecture number 7, EELS Advisor. My name is Nanda Menon. I am the System Software Engineering Manager. So during the course of this week at the EELS School, you will have come across a number of situations that have prompted a number of very important questions with respect to EELS microanalysis. The issue of how much of a particular element and a particular edge is detectable using EELS arises, as well as what the dose and acquisition time constraints are for detecting a particular edge. And you'll have understood that the answer is really a complicated interplay of many effects. So, for example, there are many situations where the visibility of an edge might be dictated by the surrounding edges and how long we're willing to acquire at that edge. And we also know that the quantification, once we've recorded the spectra at that edge, the quantification will depend on how we choose to configure our background and signal windows for extracting the signal and for coming up with a quantitative measure as to the concentration of a particular element. The EELS Advisor software is designed to provide some guide for users of the EELS technique as to what the result would be when performing a given EELS experiment. This was software that was developed many years ago, and it was essentially used as some kind of indicator as to what the outcome of an EELS experiment would be. So what is EELS Advisor? So EELS Advisor is basically a software package that provides an a priori guide to perform a given electron energy loss experiment. Using EELS Advisor, the user can visualize the form of an EELS spectrum for a given sample in experimental conditions. And based on that, the user can decide if the chosen experiment is feasible or whether or not there are certain constraints that prevent a given element and edge being detectable using EELS. Furthermore, the software has optimization routines that are built in that allow for the determination of optimum acquisition and processing parameters that can be used to yield reliable results. The software covers different signal types and includes spectroscopy and 2- and 3-window mapping. So just to introduce the problem, a very common question, some common questions that arise in EELS microanalysis are the following. So here I've shown you an example of, on the left-hand side, a spectrum which contains nitrogen K-edge at 401 eV and at nitrogen at 5 atomic percent, lying on a background that is predominantly from a carbon matrix. So on the left-hand side, you can see that this edge is clearly visible above the background, even though the spectrum is quite noisy. If you look at the spectrum under the same acquisition conditions, but at 1 atomic percent of nitrogen, you can see that the edge is barely visible over the noise. So you can't really detect that particular element in that case. So in this case, there are a number of questions that arise in this situation. So given one such question may be, given the probe current, what is the minimum acquisition time required for detection of a given element? What primary energy and convergence angle should be used? and that's what basically combination of acquisition parameters do we need to maximize this edge? And once we've grabbed our spectra, what are the signal and background parameters necessary to position to quantify that particular edge? And once we've quantified it, what is the minimum detectable mass fraction of that particular element? So these are some of the questions that EELS Advisor is attempting to answer. So the calculation details for EELS Advisor is given by this reference from a paper over 10 years ago. And basically, the foundation of the software is being able to synthesize various components of the spectrum, from the low loss, the zero loss, plasmon, and core edges, being able to piece together these components of the spectra to yield a complete spectrum that is representative of the system. We won't go into the details as to the calculation, but instead we'll refer you to this paper if you are interested. The software is written for digital micrograph and is compatible with all GMS software. Currently, several spectra can be computed per second using the software, and basically the main interaction through the software is through the palette that you see here. This EELS Advisor palette is basically the main interaction between the user and the software. So I'll go ahead and show you that directly here. So this is digital micrograph with the EELS Advisor palette open. So you can go to access it normally. You can go to Window, Floating Windows, and EELS Advisor down here, and that will launch this palette. And you can see that the palette can be summarized by this box item here that has the parameters that are used for the software. The sample, the user can specify an arbitrary sample. In this case, it's the default that we have when the software first runs is boron nitride with a trace amount of carbon at 20 nanometers thickness. The acquisition parameters are primary energy of 200 kiloelectron volts, collection angle of 10 milliradians, probe size of 1 nanometer, probe current of 1 nanoamp, and acquisition time of 1 second. And basically, this is a summary of our sample and our acquisition conditions. Okay, and at the bottom of this palette, you can see 3 buttons: Simulate, EELS, and OptiMAP. Simulate basically does just that. It simulates for these conditions what the form of the energy loss spectrum will be. And EELS and OptiMAP I will discuss a little bit later. The tools buttons you see here allows for, when you select that tools button, it launches this dialog that allows you to specify parameters for used in the calculation. So when you hit the tools button, you have 4 tabs: specimen, experiment, simulation, and optimization. Under specimen, we have this list box here, which shows the elements, the type, whether it's major, minor, or trace, and the relative concentration. In this case, we have a large amount of boron and nitrogen at 48% and a trace amount of carbon at 4%. There is a capability to edit the sample, so you can just hit Edit Sample, launches this periodic table dialog that allows you to adjust the elements that are present in your sample. There are buttons that allow you to save and open a sample at a later stage. And there are ways that you can specify automatically the concentration of particular elements by adjusting these radio buttons. So these radio buttons are useful if you don't know what the true concentration of a particular element is in your specimen. So you might want to just have the software come up with some set of defaults for you. You can also manually edit the concentration by hitting that box, the button adjacent to the value here. The sample thickness is 20 nanometers. That, again, is an input parameter used in the calculation. If we go to the next tab, we can see experiment. So experiment basically refers to the illumination and collection conditions that are used for the calculation. So the illumination conditions, we have the primary energy, probe diameter, probe current, illumination angle. And for collection, we have the collection angle. This is actually the semi-angle, as it is for the illumination, the acquisition time, the energy resolution, and the DQE. If we hit the simulation tab, so this is if you want to play around with some of the parameters that are currently used in the simulation. So I mentioned before that the basis of EELS Advisor is being able to simulate the different components of the EELS spectrum. So we have certain defaults that are used in the software for the simulation model and for the plasmon parameters. But we do allow for the user to play with these parameters to see if they can refine it for their particular sample. So we have a default model for the plasmon. We have a plasmon position and width, but it's an editable field. So it's possible to adjust these parameters to try to come up with a better model for the system. The core edges that are shown here, in this case, the sample is boron nitride with some carbon. So we have the boron K edge, carbon K edge, and nitrogen K edge as the edges here. And it's possible to choose the cross-section model for each of those edges. The software comes up with a set of defaults. For K edges, it uses the Hartree-Slater. But we also have a database of experimental defaults that can be used. And these are sometimes useful when we have edges that are difficult to model using the Hartree-Slater model. So in that case, the software will automatically point to these experimental defaults. There is also a capability of using user-defined cross-sections where basically if you have a cross-section file at a particular location, we can have the software point to that file and use that file as the basis for the calculation. And this again is useful if, for example, you've done some work or you know of some work that has modeled a particular edge or edges for a particular element, and we have a DM3 file variant of that model, then we can use that in the calculation instead. But if the details of the calculation are not accessible or not important for you, you can always rely on a default set of parameters that the calculation will use. The optimization tab I will discuss later. So once we've set up the sample and we set up the acquisition conditions, we can go back to the EELS Advisor palette and go to the button at the bottom hitting suggesting simulate and hit that simulate button. And this generates a spectrum here that shows the boron in this case at 188, the small amount of carbon, and nitrogen at 401 EV. And we can essentially play around with that a little bit by going into the tab, adjusting the acquisition time, for example, and coming up with a spectrum that maybe shows a little bit more noise, and shows the effect of basically changing the acquisition conditions on the form of the resulting spectrum. So you will have, during the course of the school, you'll have an opportunity to work through the EELS Advisor exercise. In that case, you're able to play around with these acquisition and sample parameters and get a feeling for how these parameters can influence the form of the resulting spectrum. So that's the basic EELS Advisor. So as we mentioned before, one of the important aspects of the software is optimization. So we know that the EELS spectra that we get in general are very much dependent on what the sample and acquisition conditions are. And this is illustrated here in this example, which shows a phosphorus impurity embedded in a 10 nanometer carbon matrix. In this case, the primary energy is 80 keV. The collection angle is 30 milliradians. We have 0.4 nanoamps of current and an acquisition time of 0.8 seconds. On the left-hand side, you can see the signal-to-noise ratio for one atom of phosphorus as a function of the probe diameter for the system. So you can see that as the probe diameter goes less and less, the signal-to-noise really increases. As the probe diameter increases, you can see the signal-to-noise really diminishes significantly. So having a small probe will definitely improve our detectability for single atom detection. What about the dependence of collection angle? Here you can see the signal-to-noise ratio as a function of collection angle for the phosphorus atom. So you can see that at low collection angles, we have a low signal-to-noise ratio, and then it increases so that beyond 20 milliradians, it plateaus. It seems to plateau, maybe diminishes a little bit as we go up to higher collection angles. So the signal-to-noise ratio variation provides a motivation for estimating the optimal conditions for EELS acquisition. And that is the basis of OptiEELS. So the OptiEELS software is basically optimizing a spot EELS analysis with a focus probe. So in this plot here, you can see the convergence, the probe focused on the specimen. We have a convergence angle, a probe diameter, a sample of a given thickness and composition, and a question that arises that suggests what collection angle that should be used in that case. And once we've grabbed the spectra, when we want to quantify a given edge, we want to see how the background and signal window should be used to make sure that we can get reliable results. So if we revert back to digital micrograph, we can see the presence of this OptiEELS button in the EELS Advisor palette. And to configure that, we hit the Tools button once again and go to this Optimization tab. So let's say we want to look at the optimization at the carbon K edge. So in that case, we simply go to the Optimization tab, we select the carbon K edge, and we check the Optimize checkbox. When we do that, you can see that the parameters below are enabled. And in addition to the parameters being enabled, you can see the checkboxes are all selected and set to on. What this means is that the software will now allow the collection angle, the background position and width, and the signal position and width to vary. So what it does is the software comes up with some optimization routine by varying the parameters that we specify in this box to come up with the optimal configuration of these parameters to generate the maximum signal at that edge. So for the carbon K edge, let's allow all of these parameters to vary and hit OK. Let's operate with the acquisition conditions that we already have. We know that our sample is fixed, and we can go ahead and hit the OptiEELS button. So in this case, what's happening is that the software is going through multiple iterations and coming up with a configuration of acquisition and processing conditions that maximizes the signal-to-noise ratio at the carbon K edge. So finally, the software comes up with this report that shows the edge, the elements, and the optimized spectrum. So it gives a summary of the spectrum, the specimen, which is a 20 nanometer thick, with 48% boron, 48% nitrogen, and 4% carbon. These are the beam parameters, 200 kV, electron dose, and dose per unit area given. And for these optimized conditions, it gives the expected signal-to-noise ratio, the minimum detectable atomic percentage at 3.4%, the minimum detectable number of atoms at 33, and the minimum acquisition time to detect 4% carbon for this current is 0.81 seconds. The optimum parameters, it gives the optimum collection angle at 26 milliradians, the optimal background width, once we've grabbed the spectrum of 48 eV, and the optimum signal width of 65 eV. So it basically suggests a large background and signal window. You get as much signal as possible inside the quantification window, and a large background window so that you can generate a good fit in the vicinity of the edge. And the important point is that these answers will depend quite critically on what the acquisition conditions are and what the sample is. So if you have complicating effects associated with adjacent edges, then the answer for detecting this amount of carbon will differ. And this is really where the software stands out. It's aimed to provide the user with some guide based on what the parameters are that you're dealing with in terms of the sample and the acquisition conditions as to what you can expect from your EELS experiment and how best to optimize the data that you gather. A generalization of the OptiEELS concept is found in OptiMAP, and OptiMAP is basically an application of the EELS Advisor software for 2 and 3 window mapping. So in this case, as we look at this plot, we show a parallel beam of illumination. We have a GIF, which produces a spectrum at the slit plane, and we have quadrupoles, a lens system beyond the slit plane that generates a magnified image on the CCD. And the question in this case is, how should we configure the slit and the background and signal window positions in that case to yield a good map? So once again, we can go back to digital micrograph. We can specify the parameters here, and in this case, we will typically be having a much smaller probe current because it's essentially the probe current per pixel. So typically, we'll have something like a picoamp. And in that case, we can hit OptiMAP, and it'll go through the optimization for that edge and come up with an answer. And it suggests in this case that the signal-to-noise ratio is quite small. We have a large signal-to-noise ratio resulting from the low impurity concentration, and we may have to repeat the optimization by using a larger concentration. So we can go ahead and do that. Hit the Tools button, hit Edit Sample, or change the sample concentration. You can hit carbon at 15%, hit OK. So in this case, we can go back to the EELS Advisor palette and hit OptiMAP once again. In this case, the carbon K edge becomes clearly visible. It goes ahead and does the OptiMAP, and you can see the signal and two background windows present. And it computes the expected signal-to-noise ratio for mapping, the optimal collection angle, the optimal slit width, and the optimum right background position. So basically in this case you can see that the optimum solution suggests that the two background windows should overlap with one another. So those are the main features of the EELS Advisor software. So we have the simulation, which is used as the basis for the optimization at the edge. And the optimization works in different spectrum modes. It works for both the single particle analysis and for mapping in the 2 and 3 window case. So there are a bunch of different applications that we have used to test the simulation software, and one such application was the trace phosphorous quantification in biological macromolecules, and this was done experimentally by the work of Leapman and Rizzo many years ago, 1999. So in that case, they were able to detect single atoms of phosphorus in these biological macromolecules. To model that system, we have a 3-nanometer carbon film in EELS Advisor at 0.5 atomic percent of phosphorus, 40 keV incident energy, and an acquisition time of 0.8 seconds. We run OptiEELS at the phosphorus L23 edge, located at 135 eV, and the model gives us a minimum detectable number of atoms of 1.3 plus or minus 0.2. So the EELS Advisor software is predicting single atomic detection. If we look at the output, here's a sample of the output here. We have the signal-to-noise ratio of 6, 0.4% atoms detectable, 1.3 plus minus 0.2. We have optimal parameters of 19.2 milliradians, background width of 14 eV, and signal width of 12 eV, 12.8 eV, which matches very closely with what they did experimentally. So this was a good example of a situation where the EELS Advisor provided output that was very consistent with what they observed experimentally. In addition, one further application is for overlapping edges. So in this case, we have titanium oxide with vanadium at 10%. We can run a L23 quantification, use experimental default cross-section to account for the white lines, And the results of the OptiEELS will show the presence of nearby edges. So we have the optimum parameters, the optimum background width of 10 eV, signal width of 8 eV, and basically showing that the background and signal windows are constrained somewhat when performing a quantification. And this is because of the presence of these adjacent edges, the titanium L edge at 456 eV and the oxygen K edge at 532 eV. This additional output, which once again you can investigate in the EELS Advisor exercise, basically allows you to explore the parameter space to see how the signal-to-noise ratio changes with respect to changing any one of these parameters. An example that is relevant to biological EELS is the calcium quantification in carbon. So in this case, it's total dose sensitive. So in the sample, we have 1 atomic percent of calcium and 99 atomic percent of carbon. We have a primary energy of 100 kV, current of 1 nanoamp, a 10 milliradian collection angle. We can run OptiEELS for varying thickness and observe the minimum dose required for detection. So we run OptiEELS multiple times and we can come up with a little table like this, a little graph here that shows the minimum dose required for detection as a function of the thickness. See, at small thicknesses, we have few atoms, so we need a larger dose to detect. For large thicknesses, we have multiple scattering, and we have an increased dose required for detection. And there's a broad area between 20 and 80 nanometers in this case, where we can really reduce the dose in order to be able to detect the atom. So in conclusion, EELS Advisor is a software tool that is designed to guide users in acquisition and processing EELS spectra in advance of actually performing the experiment. It is generalized to arbitrary specimens and signal types. So the user has complete flexibility in determining what specimen and what signal and what acquisition conditions will be used in the experiment. And the simulations show reasonable agreement with experiment. So the idea with the EELS Advisor software is to provide some guide that gives, within a factor of 2 or 3, that gives an idea as to whether or not a given element is detectable. And that was really the basis for the software. We wanted to provide users with some guide as to what the outcome of the energy loss experiment would be. The software features include the determination of the signal-to-noise ratio, minimum mass fraction, minimum detectable number of atoms for a supplied specimen and acquisition conditions. It also has tools for estimating the optimal parameters for processing and acquisition, and also the sensitivity of the signal-to-noise ratio to the precise parameter values. There are numerous applications of the software for quantification of trace elements, for calculating optimal windows for elemental mapping, and estimating errors. And in particular, it's useful for studying the feasibility of EELS as a technique for microanalysis. This concludes the lecture.